Good afternoon, everyone. Thank you very much for coming today and your attention. So I'm Ken from New York University, Abu Dhabi. I'll be presenting on origami-based haptic local anesthesia syringe simulator. For today, I would like to introduce my work in the context of medical simulations and origami-based haptics, and then go through the design and characterization of the constant force feedback that we want to look for in our particular application. And this is followed by assembling the syringe into a full VR simulation. We also go through our expert feedbacks from NYU's College of Dentistry, finally ending with some discussions and conclusions. So virtual reality and haptics in medical simulation has long been a very hot topic. And in our case, in our lab, we primarily focus on dental simulations, a few tasks, but one that we looked into in particular was this activity where you have a local anesthetic injected into the back of your teeth. So it's called the inferior alveolar nerve block procedure. So you basically try to inject a nerve in the back of your gum. And well, some existing works try to do this through also through haptic devices. It has been quite limited in the sense that it's either putting an actual cartridge syringe onto a digital to magic touch device, or just using a VR simulation with hand controllers with buttons and such. So what we really want for this particular activity is to have this force feedback from this plunging sensation. And as you can see, we've measured how the force feedback goes when we push the syringe. So it is a bit bumpy, but perceptually speaking, this is pretty much a constant force feedback. And this is not something you can do by just slapping on a normal spring onto a device, because that follows Hooke's law. So what we instead have is an origami-based solution. So why origami? So origami-based concept allows us to essentially lower the cost, make a more reconfigurable passive device, miniaturize it, and make it scalable in terms of the fabrication. And we'll go over that one by one. So in terms of using origamis, we employed this particular pattern known as the Khazaaleh origami pattern, seen in this paper model in the figure. So this pattern, you can actually easily recreate it by twisting a cylindrical piece of paper, and it basically just makes that by buckling. And the nice thing about this pattern is that by tuning in geometric parameters such as the height of the spring, or this radius, or the initial twisting angle, you can simulate different kinds of restoring force when you press it. So the plot shows some examples of the patterns in terms of the restoring force versus displacement. We particularly focused on a configuration that allows a constant force feedback. And of course, we don't want to use a paper because it breaks it almost instantly, so we replaced it with a combination of plastics and rubber. So essentially, we're tuning parameters from the paper model as well as some thickness of the rubber or its width, and then we 3D printed this on a polyjet printer, Stratasys J750 in particular. To extend this on an actual syringe shape, we of course had to stack the spring. So we first simulated its force displacement profile on a single unit, and then we extended to the full stack. And we first simulated this through a finite element modeling, and then we tested this with a mechanical tester. And once we've done this, we've now assembled a full haptic syringe. So to do this, we've also 3D printed a certain shaped enclosure around the spring. And this one we printed with a nylon printer to minimize the weight. And once you have a plunger, basically that's the syringe itself. To track the motion of the syringe, we coupled it with a linear soft potentiometer with some pogo pins so that when we slide the spring, and basically just nudges onto the potentiometer. So in essence, it's pretty cheap solution. So it's with the linear potentiometer and the 3D print, it's basically like below $20, and it's also reasonably small. And then we had this syringe. So we just like last time, put it on the mechanical characterization. So we characterized the syringe itself and the bare origami spring, as well as the real carpio syringe that dentists actually use. So what you see here is another force displacement profile. So I'll explain the carpio syringe first. What you see in the first spike is basically corresponding to the rubber part of the canister. So when you first plunge, you basically pierce through this rubber part in the syringe. So basically that's kind of outside of the actual anesthetic injection. So basically we omitted that. And the usable range is basically the yellow highlighted region, which corresponds to like around 30 millimeters of linear space. So the other measurements, namely the bare spring and the actual syringe, also follows the like 1.6, 1.7 Newton range of force. And as you can see, it's pretty constant. It follows the actual syringe profile as well. And just for completeness, the spike on the 30th millimeter mark, it just happens because of the small collision and the plastic guys kept on the spring stacks, like the white part, basically. So that's also kind of not relevant. So once we did the characterization, we did the more fun part, which is integrating it to the VR simulation. So this video is just to show the syringe and the virtual environment looks like. So of course the translation and rotations follow nicely, but the most important bit is the plunging motion. So because it's a linear potentiometer, the mapping is pretty smooth. So no surprise there. And in terms of the actual VR simulation, we use the existing VR simulation from the dental college that does the actual inferior alveolar nerve block procedure. We took this setup to the NYUAD College of Dentistry to have some dental professors do some trial runs on it, and we got 5 professors with 10+ years of experience to try on it, and luckily they liked the experience. So before this, they were using basically a setup without the syringe. They were just using this handheld controller with buttons to simulate the sensation of injecting. So compared to that, it was a real improvement in their training experience. And in addition to that, they asked for more hardware improvements, such as the sensation of not just penetrating the gums through the needles, but also being able to anchor the needle point, because that requires torque feedbacks. So based on these results, we would say the origami and carpio syringe force profiles were perceptually similar, and we had good positive expert feedback. And now in terms of hardware improvements, though, of course, like we can improve in terms of the 3D printing ability. So that means using a 3D printer that can print smaller syringes, not just small, but also light. And we can also add additional haptic experiences. So for example, if, for the people who already tried the actual syringe, the syringe can also pull back, and that corresponds to like a blood retraction procedure. So we can add haptic sensations like that, and of course extend it to a wider variety of medical training applications. So to conclude, we designed an origami syringe, we characterized it, integrated it to VR simulation, tested with experts, and as a future work, we plan to extend this interface to dental students, mainly in the first and second year, and then to also work on the hardware improvements. Thank you very much for listening.